All right, in the previous lectures, we were starting to discuss about the nonlinear stability theory. So we had kind of taken a break off from the guidance systems that we were talking about, and we had come back and wanted to learn about the nonlinear stability theory because some of this will be useful when we want to prove that certain guidance laws are stable enough. So in order to prove that stability, we needed to get the mathematics of the stability theory down, and which is what we were discussing in the last class. So we're looking at the so-called Lyapunov stability for the autonomous systems for now, and as we progress further down the line, we will look at for the non-autonomous systems as well. The idea simply being here is that x dot is equal to f of x. You do not see a explicit dependence on time. That is what it means as an autonomous system. When I say a non-autonomous system, it means that it will have an explicit dependence on time. So x dot will be f of x comma t. Okay, so time might come into the picture. And a quick example of a autonomous system is a spring mass damper system, which we saw previously. Can you give me a quick example of a non-autonomous system? Really that hard? It's not.
Forced spring mass oscillator.
Bingo. You can just add a forcing term to the spring mass damper system. Now your system dynamics actually has an explicit dependence on time. The force is actually time varying. So now you start to see a non-autonomous system in that case. Okay, so first we'll discuss about the so-called autonomous systems first because they are the simpler lot. Then we will extend the ideas that we discussed for the autonomous system to the non-autonomous system. So last class, I think we started off with this idea that whenever we are looking at this initial value problem, x dot is equal to f of x, we also are assuming that f to be locally Lipschitz, okay? Which means that basically it is giving some bound. So we understood in an intuitive sense, we understood that it is a stronger condition than continuity, and it's a weaker condition than differentiability. So we assume that f of x is continuous, and in most cases we'll find that it is differentiable as well for most of the systems that we look at. So therefore, in that case, there is no question of it being Lipschitz. It's actually continuous and differentiable. But the theory is equally valid even when the differentiability may not actually hold. So even for such systems, the stability theory is sufficient enough. So which is why this concept of Lipschitz stability comes into the picture. So I kind of gave you a little bit of idea in a graphical sense also as to that when you are trying to see as you traverse along the function, there is a double cone which we can form, like an intersection of two cross lines, and the function will always lie to the left or the right of that double cone. It won't actually get into the double cone. That's what it physically, intuitively means. Okay, but all of that doesn't have a sense of stability. Many times students will not understand what does that mean. Okay, it's not coming into a double cone. What does that really mean, right? So think of it as a stronger condition than continuity, but a weaker condition than differentiability. But also please understand that for most of our cases, the f of x will be differentiable in most cases. Okay, unless we are dealing with some really weird processes, we will be mostly having a continuous processes and a differentiable processes. Okay, then we started the idea that we are looking at the equilibrium point of this system, and we were understanding that xe, let's denote that as the equilibrium point of that system. Then f of xe must be equal to 0 by definition of the fact that it's an equilibrium point. Okay. Then we discussed about the idea of boundedness. So the solutions of x of t are bounded if there exists a non-negative function such that the norm of x is always less than equal to some gamma of x0. So when I pass it through that function, the initial condition value, it defines a big range of radius, or not necessarily radius, but a region in space. And I'm assuming that my future solutions are always going to be inside that bounded region. So for example, let's say if it's a two-dimensional system, so I'm kind of saying that, let's say I have some region defined, and that is what is being given by your gamma of x of 0. And then let's say x of 0 is somewhere here. Okay. And then as the system evolves over time, no matter what it does, it doesn't cross this boundary is what I'm saying. Okay. So the solution space never crosses over this boundary line, then the system is bounded. Is everybody with me? Yes, no?
Yes, sir.
All right. Then we were discussing the idea that an equilibrium point is stable. So an equilibrium point xc is stable if for each epsilon greater than 0, there exists a delta greater than 0 such that x0 minus xc is less than delta implies xt minus xc is less than epsilon. Now, this definition can seem a little out of place, but what it essentially means is that suppose I have xe as a point here, okay, let that denote xe. So if I start inside some ball of xe, so let's call this xe. So I start inside some ball, then I can say that x of t minus xe will lie inside another ball which is having a size epsilon. So this is delta, whereas this is epsilon. So it is telling me that if I start inside some region here, if I can find a bounding boundary saying that it stays inside certain other region, okay, then the system is stable. Is everybody with me here? So the idea of stability doesn't necessarily mean that we should reach the equilibrium point. That is not what an stable equilibrium point is telling you. It doesn't say that over time I will just stay at xe. Nowhere am I saying that. As long as I start at a point, so suppose I want to keep my solutions under this ball of epsilon, the idea is I can find a smaller ball delta, which may depend on epsilon, such that as long as I start inside of that ball, my solution stays inside this bigger ball. That is the concept of stability. Is that making sense for everyone?
Yes, sir.
Yes? Everybody is comfortable with the idea?
Yes, sir.
Stability does not necessarily mean that we have a direct convergence onto the equilibrium point. Doesn't necessarily mean that. Okay. All right. And we define so that's a stable equilibrium point. So what is an unstable equilibrium point? It's very simple. A equilibrium point which is not stable is an unstable equilibrium point, which means that if I want to keep the system inside a ball of epsilon, but I can't find a delta such that the system stays inside epsilon ball over time, then I call that system as unstable.
So,
Yes.
sir, what if we make that epsilon value bigger so that it fits into that ball?
What is?
What if we make that epsilon bigger so it fits into that epsilon ball?
What if we make, I didn't follow your question. Come again, Anand, tell me again.
Sir, what if the epsilon is big enough so that it fits into that ball?
Epsilon is something you choose. See, the point is I want my solution over time to be inside the epsilon ball. Now my target is to find a delta such that my initial point should be inside some smaller ball such that the solution doesn't leave the epsilon ball. If I can find a delta like that, then that system is stable. That equilibrium point is stable. If I can't find a delta, then it is unstable. That's all it means. Which means that if I want to keep the solution inside epsilon ball over time, but I can't find a delta such that these small starting points will ensure that that will happen, then such a system is called an unstable system.
Yes, sir.
Okay, but I am not quite sure I answered your question. Can you repeat your question one more time? I didn't quite get you actually.
Sir, what I was about to say is if we make that epsilon big enough so that the function fits into that epsilon, so is it possible?
Yeah, so the epsilon is arbitrary. See, it is not talking about how big or small epsilon is. It is saying that given an epsilon, can I find a delta or not? So
Yes.
Given a finite value of epsilon, can I find a delta such that when I start in from that delta, my solutions will remain inside the epsilon ball? Now, your idea is that suppose I make epsilon infinite. That's what you're thinking. Am I right?
Yes, sir.
So if I make epsilon infinite, then the system has to be always what you call, no matter where I start, it will be the case. No, that's not the point. Because generally, even if you are looking at a infinitely large, we are looking at compact sets. So from a mathematical standpoint, the infinity point itself is usually not a part of your set. Okay, and that will lead to more mathematical issues, okay, sort of, in the sense that if I start at infinity, I continue to stay at infinity. So it's as if it's like an equilibrium point there already.
Yes,
right?
got it.
So those concepts start to come at play, and now that becomes a more nonlinear dynamics theory class, nonlinear dynamical systems class, which this is not. So we'll try to refrain from going in that direction. But at least you understand the concept or intuitive understanding that if I have a epsilon ball in which I want to keep my system's trajectories over time, I will be able to find a smaller ball such that when I start inside that smaller ball, I'll always be able to keep inside this epsilon ball. And if it is an unstable system, you can't find a delta. That is the point. Okay?
Yes, sir.
Okay. Our equilibrium point is called attractive. Okay, we call it as an attractive equilibrium point if for each r greater than 0, so some radius that I'm choosing, there exists, okay, a time, capital T, which depends on r and epsilon, such that if I start with the initial condition which is closer than r, it will result in my system being inside that epsilon ball for all time greater than this time t. So you'll see that here it has a similar idea of what was a stable system. Only thing is that it is saying over a certain period of time, okay, the system will necessarily stabilize. Okay, if I start inside this region, okay, it implies that the trajectories will be inside epsilon for all time t greater than capital T of r comma epsilon. So this function of r comma epsilon is the key difference between what we saw before. Previously, when we looked at systems with stability, we were simply talking about as time goes beyond We just want to keep the trajectory inside that bounding box. Here we are saying that the system is attractive if there exists a t such that as this is less than r implies that this is less than epsilon for all time greater than this value of t, which depends on r and epsilon. A corollary of it actually is that what this statement probably is not directly telling you is that we intend for this system to reach the equilibrium point as time tends to infinity. That is when we call the system as attractive. Okay. So attractive system simply means that the stable equilibrium point is actually attracting all the trajectories towards it. Then we call such a system as attractive stable equilibrium point. Is everybody with me? Don't think about the mathematics, think about the intuitive sense. An attractive equilibrium point simply means that it's trying to attract everything towards it. So in the limiting time t equal to infinity, we expect the trajectories to end up at the equilibrium point xe.
Sir, so this is like asymptotic stability or?
No, this is not asymptotic stability. I'm not talking about asymptotic just yet. It is just talking about the attractive stability. It may be asymptotically stable or it may be exponentially stable. Both of them will still fall under the attractive stability. All I am saying here is simply that the fixed point or the equilibrium point is attractive in nature. How attractive it is, whether it is exponentially attractive or is it asymptotically attractive, I'm not talking about that just yet. I'm going to talk about that in a little bit. Here it is, I'm only talking about the idea that it is attractive.
Yes, sir.
Everybody with me? Okay, all right. See, these concepts which are coming as these inequalities, they are simply mathematical definitions of stability. I want you to rather have a more intuitive understanding of what it physically means in the phase plane, okay? Rather than thinking too much about the mathematics of it, it is important to have an intuitive understanding of what we are looking at. Because this is not a class on mathematics, we need that intuitive geometrical understanding in order to appreciate what's going on. Okay, now we will talk about asymptotically stable systems. So if the equilibrium point is stable and is attractive, then the system is asymptotically stable, which means it is attracting and the system is stable enough, which means that if I come and stay on the system, I typically continue to stay on the system and small perturbations from the system continue to keep me in the vicinity of the system. Okay, that's what it's saying. So as long as a system is stable and attractive, that means it's an asymptotically stable system. Notice that there is something here I written as locally asymptotically stable, because a globally stable system, if Xe is a globally stable system, then this delta of epsilon can be chosen to satisfy infinity, which means I can start anywhere in the phase space and that system can be shown that over time it will come inside a certain region of trajectory. Okay, so as long as what this is saying is, let me put my pointer here. Okay, for simplicity, let us consider that if the equilibrium point is at the origin, okay, then I am saying that this epsilon ball, inside that I want to be, what is the delta ball that I require? That is what was the idea of stability primarily, correct? Here what I'm saying is, as epsilon tends to zero, as tends to infinity, delta also will tend to infinity. Okay, if epsilon tends to infinity, then delta also will tend to infinity. Because if I want that system to be inside a ball of infinity, then I'm saying that as long as I can start from anywhere inside the trajectories, I can still be inside that infinity ball, then that is globally exponentially stable. Are you following me? Okay. All right. Then we come up with the idea of globally asymptotically stable. Okay. Remember that previously we talked about the idea of locally asymptotically stable. Now we will discuss about globally asymptotically stable. Okay. Is everybody still with me, or there is some confusion going on? Because I'm looking at a few confused faces. Now's the time to ask.
Sir, could you please explain that local and global phenomenon again?
See, local stability means that if I want to choose a value of epsilon and I want this system to find out a delta such that when I start inside this delta ball, I continue to have my trajectories inside that epsilon system, then such system is simply called locally stable. Okay, but what the globally stable means is I can now start making these epsilons really big. There is no necessity to hold down that epsilon must be a small number. If it holds for very, very large numbers where epsilon tends to infinity also. Okay?
Yes.
In that case, I'm saying that my delta also should tend to infinity.
Our delta? Sorry.
Delta also will tend to infinity.
Okay. So no matter wherever we start, we will be inside that epsilon ball.
We can always be inside that epsilon ball. So basic idea is no matter how big the epsilon is, I can always find the delta corresponding to that epsilon where I can be in the ball. Otherwise, locally is a weaker statement. It means that let's say that there is some epsilon max. Okay, beyond which let's say this doesn't hold. If I want to keep the system inside a ball of epsilon max plus 1, let's say, for example, I can't find a delta, let us say, right? Then that system is locally stable only. It's not globally stable. Globally stable means I can make that epsilon arbitrarily large and I can still find a delta. And as epsilon becomes bigger, so does my delta also become bigger. That's what it's saying.
Yes, sir. Yes.
Okay, it is only a concept of stability here we are talking. No asymptotics. Okay, this is only locally stable versus globally stable. Idea is the same. Only thing is I can make my epsilon arbitrarily large.
Yes.
Okay. Now, when I talk about the so-called asymptotic stability, I'm now talking about the attractive nature of the stability point. That does it actually attract towards it? Does it actually attract the trajectories towards it? Then only it is asymptotically stable. Which means, if you look at the idea that if I have, let me put a page here. Yeah. So when I have my spring mass damper system, mv dot plus kx is equal to 0 and v is equal to x dot, or x dot is equal to v. So I knew that we could write this down as a state space, right? Is equal to v, and v dot was minus k by m times x. Now, what is the equilibrium point for this system?
0, x equal to 0.
V equal to 0 and x equal to 0, right? X equal to 0 and V equal to 0 is an equilibrium point. So Xe is equal to CE, same. That's equal to basically 0, 0. Now, if I want to identify the stability of the system, okay, if I now take a small ball of epsilon and I say I want to keep the trajectories inside that epsilon ball, okay, so what am I looking at? I'm looking at a phase space. So generally a phase space refers to a plot of the two states that you have. So in this case, it is a state X versus V. Okay, this is what is called as a phase plane. This is what is called as a phase plane. And it is in here that we want to look at what is happening to the trajectories over time. Notice that this is not a plot versus time. We are looking at what is happening to the trajectories starting from an initial condition. So if I start from some initial condition and I let go of the system, what will happen? How will the trajectory evolve on this phase plane? I basically pulled it by a distance x and I'm letting it go. How will the plot look on the phase plane?
Go down and left.
Sir, it will go down negative.
It will go down and then, so it will start here and it will go down, and then what will happen?
First of all, it will be on a circle.
Yes, it will be on basically a shape which
It will be a circle. It can be ellipse also, right?
Oh, yeah.
could be an ellipse as well. It need not be a circle. It actually will not be a circle. It will most
It
likely be an
will
ellipse.
depend on the parameters. Yes.
Okay. So what's happening now? Which direction is it going around, in the clockwise direction or the anti-clockwise direction?
Twice, right?
It's going in the clockwise direction. Why?
Because for a positive x, when you are leaving it, it will have a negative velocity, right? Like in the direction of x, right?
Correct. So when I stretch it and let it go, x is positive, but the velocity is negative.
Okay.
The velocity will be in the opposite direction when I let it go. So at that, the velocity will be in this direction. So that's why you will see that it will start off in this direction and keep going around. Okay. A usual measure of sense is that you'll always see that if I plot that so-called vector field, which means that at so many different points I'm looking at what is happening to the vector field, you'll see that they'll basically be governed by small little arrows. So on and so forth, right? What it means is that wherever V is positive, it's as simple as this. If V is positive, then X should increase. So therefore, most likely the arrow will point this way. It's unlikely the arrow will point behind, right? But it can, depending on how I define my states. So for example, if I had defined V equal to minus X dot, one of the states of my system was defined as V is equal to minus X dot, or X dot equal to minus V. Then the thing will point in the opposite direction, right? So you have to be kind of careful. Generally, we won't do that. But in case if the states are more complex than a regular derivative, then you have to be careful about what is happening to the vector field. Okay. So in this case, what is happening, no matter where I choose my initial condition, I can never exceed the value of x corresponding to that. So for example, if I choose the initial value here as x0, I know that my epsilon limit is this. Isn't it? Yes.
Yes.
Yes, sir.
Okay, and as long as that chosen epsilon is taken, I can figure out a value of values of what you call delta, such that I'll always be inside it.
Sir, so epsilon is a scalar, right?
This is scalar value, right?
And
Same.
delta it might be a vector.
No, delta also is a scalar value. I'm always considering both of them to be norms, right? Norm of x minus xe, norm of xt minus x.
Okay, normal, yeah.
I'm basically looking at what is the vector pointing to the new position, how big that vector can get.
Okay, yes.
Okay. So in this case, is the system stable?
Yes, sir.
For a chosen epsilon, can I find a delta?
Yes, sir.
I can always find a delta. Is the system attractive?
No, this is not attractive.
This is not attractive. Not all trajectories are leading into the endpoint. In fact, if I start on any of these paths, I'll keep rotating on this path infinitely, but I'll never get to the origin point, which is my equilibrium point, right? Now, if in addition I made a small change that x dot is equal to v and v dot plus b times v plus k times x is equal to 0. So all I have done is add some damping to the system. Now what happens? The system now dynamics x dot v dot is equal to v and minus k by m times x minus b by m times v. That's what I get out of it now, right? If I now start looking at the phase plane diagram for this system, what do I expect to see? When I start from, just like before, I start from a point here, what do I expect to see?
Inward spiral.
A spiral.
It will be an inward spiral. So basically I start, I'm a terrible drawer on this Wacom tablet. That is how you'll start seeing the trajectories. Now, is the system stable?
Yes, sir.
It is stable here too. Given any value of epsilon, I can always find a delta such that it will always lie inside it. Right? Is the system attractive?
Yes, sir.
It is attractive. All the trajectories are converging to the equilibrium point. So this is a case where you have the so-called asymptotic stability. It is asymptotically stable. Now, also observe, is it globally asymptotically stable or is it only locally stable? Do I have to be close to the equilibrium point or can I be as far away from the equilibrium point and I'll always be still stable?
Globally, sir.
This is globally asymptotically stable. The system, I can have my x as large as possible. The starting point could be as large as possible. Yet, over time, it will come into a spiral which will dwindle down and then stop at my origin point. Okay, so this system is actually not just asymptotically stable, it is globally asymptotically stable. Is everybody with me so far? Yes? No?
Yes, sir.
Yes, sir.
Okay, so that is the primary idea, which is different between the locally asymptotically stable versus a globally asymptotically stable, is that that region of attraction where the initial conditions get attracted towards the equilibrium point is the complete real plane. So no matter where I start, I'll always be attracted to the equilibrium point. For linear systems, usually this will always be a globally asymptotically stable system, as long as it is, if the equilibrium point is asymptotically stable, it will be globally asymptotically stable for a linear system. For nonlinear systems, that's not the case. Okay, and I'll kind of give you an example right now to see and appreciate what is going on. Let us say I come back here, okay, and let's say that my system looks like x dot plus x is equal to 0. This is representing a so-called spring mass damper system, right, which you saw before. Only the value of m is 1 and k is 1 here, right? But suppose I modified this slightly and I said x dot plus x minus x cube is equal to 0. Now if I wanted to find out where the phase plane will lie, and you wanted to see what is happening there, first of all, how many equilibrium points does the system have? How do we find out the equilibrium points? We first have to express this in a state space format, right? So x dot is equal to v dot is equal to x cube minus x, right? So our f of x is basically v and x cube minus x. That must be equal to 0 for me to find the equilibrium points, correct? Which means v is equal to 0 and x is equal to
0 and plus or minus
0 or plus or minus 1, right? So I have now 3 equilibrium points. So x comma v pair corresponding to minus 1 comma 0, 0 comma 0 and 1 comma 0, right? So therefore there are 3 equilibrium points precisely here, let's say. Okay, now what happens when I have a angle which I'm starting from here? What should happen to the trajectory starting there? It's like a ship roll, right? This looks like a GZ curve, doesn't it? If you look at x minus x cube, I plot it, it looks something like that, right? Okay, so this being the angle of vanishing stability, sort of. If you look at a GZ curve of a ship, you would kind of see something like that, and that would correspond to the angle of vanishing stability. All right? So when I have displacing by a small angle and letting it go, what happens? What will happen? I displace the vessel by a slight value and let it go.
v dot will be negative.
Back.
So it will be negative.
V dot will be negative, right? V will be negative actually. Right?
Oh yeah, we also. Yeah.
You expect to see it do the same thing as before, right? Yes. So until I reach the value of 1, more or less this is the picture which we will get. Now, the moment I start at some point beyond here, what will happen there? How does the trajectory look there?
It will be positive.
V will be
Positive, I think, right?
V
V dot.
Sir, where are you starting in this case? Starting point?
Sorry. I'm starting here. The blue mark.
So here V dot will be positive here.
Hence,
V dot
we
is
gradually
positive.
increase, right?
V dot will be positive means we will increase.
Increase gradually. Will be positive.
It will be positive and we will increase, right?
Yes. And since V is positive, X dot is also positive. So X will also increase. So it will go on the right hand side and in the
Yes.
first quadrant.
Yes. And it will basically go. No, V dot will be.
V dot will be positive because V dot is X cube minus X and X is greater than 1.
So it will be, V dot will be greater than 0.
So V dot will be positive.
So hence we gradually increase, right?
Yeah, V will gradually increase. And as V increases, X will also increase.
X will also increase. So it will go.
So it will basically go like that.
Yes.
It will blow.
It will blow up, right? It will go off to infinity. Now, what happens when I have a trajectory which is behind here? Just mark it in another color. What should happen here? I want to finish this idea and stop today so that you get a sense of understanding what's going on. What will happen here?
V dot will be negative. V will be negative and hence X also negative, right?
V dot will be negative.
And so we will gradually decrease, so it will go to the negative. And X will correspondingly decrease as well. So it will
Basically
make it
this way.
similar
Correct?
to
Right. Now, if I start at some point, let's say, slightly on here. So let me come back to this plot. Okay, and let's say that I'm starting at a point way far off here. What should happen here? So I'm starting with a zero initial condition, but the velocity is negative.
yeah.
So here V dot is 0.
V dot is 0.
But V is negative, so X dot is negative, so X will decrease.
X will decrease. And as X decreases,
X will probably cross 1. So, no, negative 1, minus 1.
yeah, so it will basically
Like
go
it,
off like
yeah.
that.
Yeah.
Right? And similarly, if I have a point which is way high up on this point, it will also try to run away this way. But if I have a relatively system which is close enough, then what might happen? This fellow will still continue to do this circle thingy. Correct? There will be a point beyond which the flip will happen. Correct? And that point is basically nothing but wherever these two lines are starting from -1 and ending at 1, and similarly the other one will be a mirror image of that. Now we are talking about certain things. Okay, what is the region of attraction for the center equilibrium point? Now you understand that if I want to find the equilibrium point which is at the center, I want to find its attractive region. It is not defined here because it is not attracting for now, isn't it? Because we saw that in the as they did not have any damping, it's not attracting at all. But suppose I add a damping as well. If I say I did add some amount of damping, so some X dot, then what will happen? It will be attractive, right? But not all of the region is attractive, isn't it? there will be a region of the phase plane which is outside of this I-shaped thingy will not attract. But whatever is inside this I-shaped thing, that will get attracted to the origin. Okay? Is that making sense now?
Yes, sir.
In this case, it is not globally asymptotically stable. The origin is not globally asymptotically stable, but it is locally asymptotically stable in the sense that the region of attraction is not the complete phase plane. Everybody with me so far?
Yes, sir.
Yes. Aditya, Vallabh?
Yes, sir.
Yes. Okay. So that is the idea that here the system is no longer, it is not globally asymptotically stable, but that is where it will be locally asymptotically stable. And there is a region of attraction which we can find, which is not going to be the total real plane. Okay. I'm happy that I was actually able to cover that portion today. I'll probably just cover two more concepts and then we'll close off. So the next concept is locally exponentially stable. Okay, this means that not only is the point x of t approaching the equilibrium point xe at some over time, but it is coming so at an exponential rate, which means that the distance of the trajectory x of t minus xe is bounded by some exponential function, which means that I have an exponential convergence rate. In this case, the bounding rate is actually lambda. Okay, is that making sense? That's where I call it as it is locally exponentially stable. If the system can be expanded out, the region of attraction is the complete real plane, then the system is globally exponentially stable. Okay, no matter where I start, the region of attraction is Rn, so no matter where I start, I'll reach my equilibrium point, but at an exponential rate. I'm able to even specify an exponential rate. So between an asymptotic stability and an exponential stability, which one is the stronger condition?
Exponential.
The exponential condition is a stronger condition, right? Because it's giving you a finite exponential convergence rate, a bound on that, how quickly does it do it? Okay, and asymptotics, so you have the stability, asymptotic stability, on top of it you have the exponential stability. And all three things you have locally, all three things you also have globally. This is how we are defining stability of an equilibrium point. Okay, I hope that's kind of making sense. There are 6 things which we are looking at.
Hello?
Yes.
So, sir, this exponentially stable only defines the rate at which the system will go to the equilibrium point.
Yes,
Right.
an exponentially stable equilibrium point will be asymptotically stable also.
Okay.
An exponential equilibrium point will definitely be asymptotically stable because you are having a region of attraction. You are going to end up at the equilibrium point over time. But you're not just going there in an arbitrary manner, but you're going in an exponential manner. So it's a stronger condition of asymptotic stability.
Okay, so all exponentially stable systems are asymptotically stable also, since
But
they.
the vice versa is not true. Not all asymptotically stable systems will be exponentially stable.
Yes.
Okay, so exponential stability gives you the fact that the system is asymptotically stable, gives you the fact that the equilibrium point is actually stable. Whereas if the equilibrium point is stable, you can't say that whether the system will be asymptotically stable or not. Similarly, a system which is asymptotically stable, you can't say whether it will be exponentially stable or not. Okay, so there is a cascade: stability, asymptotic stability, exponential stability. Exponential stability means the other two exist.
Yes.
Asymptotic stability means stability exists,
Yeah.
right? But asymptotic stability does not mean exponential stability exists.
Yes.
Okay? So that is the primary idea. And you will see here for most nonlinear systems, as we saw in the case of this ship roll motion case, there will not be a single equilibrium point. There will be multiple equilibrium points. Okay, and then you have to look at what is the region of attraction of each equilibrium point in order to understand what is happening inside that attractive region. The dynamics will be very different between what we see inside that I-shaped thingy or when we are moving outside that I-shaped thing. Okay, and so therefore the dynamics exhibits much more complexity than what you see in real systems. In real systems, you'll always have only one equilibrium point. Right? In a real system means what? It's if you are looking at this so-called X vector, you are basically saying it will be some matrix A times X. That's what you're saying. That is what is a linear system. You can't have non-linearities in this system. And here we know, we have seen such systems before, the eigenvalues of that matrix A will govern what is happening to the system. If all the eigenvalues have real negative parts of the matrix A, then no matter where you start, how far you start, eventually you will end up at the origin. Okay, so these concepts will start making more sense. So these concepts of stability and asymptotic stability and exponential stability will formalize them in terms of what are called Lyapunov functions, Lyapunov's direct method. And that is what we'll take a look at on Thursday. And then we will also try to come back later on once we have covered everything. When we come back to the guidance systems, you'll see how line of sight controllers, we can kind of apply this and make sure that the system is actually stable or not. So these concepts will be used there. So have a little patience. We will start looking at that in the next class onwards. Any questions before I wind down? Anything which might be bothering you at all? No?
So,
Yeah. Tell me.
For asymptotic stability, the rate of convergence, can it be zero at any point of time, or it has to be necessarily like have a finite value at all times? Like not necessarily like exponential stability means that rate of convergence should be above or like exponential in that manner. But for asymptotic stability, should it have a finite value at all times? The rate of convergence. Or can it be like consistent like at certain points of time? Like,
No, need not necessarily have a finite value all the time. It may be zero for a period of time also.
okay, sir.
But I mean, no, if it is asymptotically stable, it will have a finite value. It will always have a finite value. Neutrally stable means it may not, it may be zero, which is in your case a spring mass system with no damper. Right?
Okay.
But with a asymptotically stable systems, you will always see that it will always converge, but you can't necessarily find a rate of convergence. You can't necessarily always find a expression for the rate of convergence.
Okay.
That is what it is telling. And exponential stability is much more stronger in the sense you can put a bound and say that yes, this thing will converge faster than this function which is exponentially decaying.
Okay.
Yeah, that is what an exponential stability is meaning. That's all.
Understood. Yes. Got it.
Any other queries? Okay. All right. So in that case, let me stop recording here.